are very trivial. We will go back to that section later when we have time. Right now, we will start from Green's theorem. Green's theorem actually is an extension of the divergence theorem. It starts from divergence theorem. Volume integration. This is the volume integration. And can be changed. Divergence A can be changed to surface integration as A dot. We learned this one, divergence theorem before. And then A can be substituted with phi gradient psi. Here we will have street notation for phi. Okay, this one is normally for potential. And this is some kind of, they are all phi. This one is reserved for coordinate system. Cylindrical coordinate. Rho, phi, z. That's Jackson's notation. Okay, because we have many phi. And this one normally later on will be used for this one. Will be a substitute for this one. That's potential. This one is to be determined. Okay. So we can simply let A equals phi gradient psi. And then divergence A gives us this one. And A dot this one gives us a shorthand notation, this one. Okay, if you don't like this notation, it's okay. You can just write it in this form. That's okay, no problem. Okay. Personally, I don't like this notation because it will be easily confused. I have no feeling. But this one I know is the normal phi gradient psi dot. This normal direction. Okay. Substitute these two into here and here. We got this one. This is the Green's first identity. Green's first identity. Okay? And then we can interchange phi and psi. Also, Green's first identity, but just change the symbol, the order of the symbol. Phi Laplacian psi. Okay, and here, psi Laplacian phi. Okay, and then subtract these two equations. And we got the Green's second identity. Okay, up to this point, we from 2 and becomes 4. We double the equation. What is the advantage of this Green's second identity? The advantage is later on we will find psi is the Green function. And psi is a Green function. So this one will become delta function. And on the surface, psi will be 0. So we will use psi is the Green function. So we will start to study Dirac Delta function. Okay, it's a delta function. And this Green function is actually related to delta function. Okay, and we will use boundary condition. Boundary condition help us to determine start phi of the side should be correct. So let me try this one. Why I want to try this one? Because I already know these relations. When I was an undergraduate student, when you were undergraduate students, you should be familiar with this notation. Because this one is related to flux. Total flux pointing outward will be proportional to total charge enclosed. Okay. So I will show you in problem 2, page 17. Maybe you can open to your page 17 and 18. I will show you how to prove this one. Page 17 and page 18. Okay, right now we can substitute any scalar function. Okay, let's substitute this one. And let's substitute phi to be potential. Potential phi, capital phi. So we got this one. This is Poisson's equation. Okay? So substitute this one and this one. So we got this one because of this one. And we got this one. So it becomes very simple. We can derive phi of x equals to this one plus this one. We saw this one before, over and over again. However, these are new. These two are new. When we are undergraduate students, we just deal with these terms. But consider infinite space, very, very large space. But now, we just focus on finite space. Finite space. Okay. For finite space, we should consider the contribution from surface. That's new. That's new. But looks very powerful, but not very useful. Why? 1, 2, 3. 3 terms. Can we simplify to 2 terms or 1 terms? 1 terms we already know. Can we simplify from 3 terms to 2 terms? Yes, if we choose the correct green function. If we choose a correct green function, then this term can be 0. If we choose green function properly. Okay, so you might expect the so-called green function has to be related to delta function, and on the surface should be 0. And then we have 2 terms, 1, 2. Okay. We can simplify from 3 terms to 2 terms. So we don't have to worry about if we want to deal with a problem locally. We don't have to worry outer space, outside this universe. Because we don't know what happened very, very far away. We have no idea. Because it's too far, right? You don't know. We don't know. We don't know. We have no idea. So, integrate the finite space is more reasonable. It's much more easier to deal with. For example, if you want to do an experiment in your lab space is not too big. You don't have to worry too much. Just focus on lab space. the volume of the left space and the surface of that space. That's it. Others, don't worry. That's good news. We can focus our attention locally. We don't have to worry about outside very much, because outside can be solved from the surface. Okay, that's the power of the green function. It's more complete because it starts from divergence theorem. Starts from divergence theorem. That's always true. And then Green's first identity, Green's second identity. Up to this point, phi and psi are arbitrary. Any function is okay. But if we properly choose phi and psi, we can simplify the calculation a little bit from 3 terms to 2 terms. If this one is 0, Laplace equation, great. This one is 0. Then we just deal with 1 terms. Good news. Good news. So we can simplify the calculation a lot. That's why we will talk about Green's theorem first. Up to this point, we have to face Dirac Delta function. So let me show you. The Dirac Delta function, you can define delta x minus a equals 0 if x is not equal to a. And if a is somewhere between a1 and a2, and then integration gives us 1. That's the Dirac Delta function. Since the delta function is defined in terms of an integration, it takes an integration to bring out its full meaning. We have to perform the integration, and then we can extract the physics meaning. This one is not well defined. It's not well defined because we don't know the shape inside this one. We have no idea. There can be any function. For example, these are approximations of the Dirac Delta function. Delta x can be this form, this form, this form. Which one you like? I know the mathematicians do not like. They don't like the Dirac Delta function. But physics like delta function very much. Convenient. Convenient. Very convenient. So we will use delta function a lot. Mathematicians say delta function is not a well-defined function. You must take an integration to bring its full meaning. Okay. Take an integration to bring out its full meaning. Now, let me show you more properties of the delta function. Just give us 1. Okay? Now, we have a function f of x. Otherwise, delta function 0, no contribution, except here. Therefore, after integration, it just gives us f of a. Okay, looks very simple. And then, the second property, first property, second property, f of x, but this time we have the first derivative, prime. 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 Delta function prime just indicates delta prime x minus a is just it's a shorthand notation. Okay. Unfortunately, later on we have two coordinate system. X observer source, we still use prime. But this prime is not derivative. So we have limited notation. This prime is first derivative. This prime just another coordinate system. Okay. Because of limited notation. Because of limited notation, so we have no choice. Okay, so be careful. Be careful about prime, the physics meaning of the prime. Here, obviously, it should be first derivative. And then f of x, delta x minus a. That's the dx. And then cancel. So, delta prime x minus a dx equals the delta x minus a. Then we can perform integration by parts. Okay? We got this one. And here and here, nothing. Because of the property delta function. 0. So only this one will survive. So eventually we got a minus sign, minus f prime a. Okay. Only when x equals a, we have value. So it's f prime a. Okay? Just like this one. But this time it's a prime. This time is a prime. Okay. That's the first property, that's the second property. What else? The third properties. The third property normally is a homework. But most of the students takes too much time to solve this problem. So it becomes an exercise as shown here. Okay. Many people, many students will be confused about the third properties. Okay. The third property is s equals a be the roots of f of x equals 0. So when x equals a, this is 0. Delta function 0 is 1. Very last. After integration gives us 1. But you can rewrite this one into this one times this one. Something like chain rule. df, and dx from the denominator becomes numerator. something like chain rule. Okay, change this one. And oh yeah. So the x equals to the f the x1 the f. Okay, that's this one. We change from the x to here. Okay. Next step is a little bit tricky. Let me show you. This is the area. How to perform the integration? You can divide it into several areas. And sum all the areas one by one. The base times height, the base times height, base times height. Just integrate. Okay? So you might imagine from here, 1 positive, positive, plus 1, plus 1, plus 1, that should be the same. All from here, just looks like A1, A2, A3, A4, 5, 6, 7. Integration just like A1, A2 plus A7. It just equals to A7 plus A6 plus A1. Should be the same. Commute. It's commute. Okay, so integration. A1, A2. So you might imagine from A1 to A2, f of x dx equals from A2 to A1, f of x dx. You might expect that, just like summation. Is that correct? Yes, it's incorrect. It differs by a minus sign. Because the x is negative, negative, negative. This one is positive. So many students will be confused here. Be careful. It's not just summation, not just simple summation, unlike this one. We have this one. Keep this in mind. Because of these terms, because of these properties, so f of x, if it looks like this one or looks like this one, it's different. It's different. Okay, let's consider this one first. The slope is greater than 0. Slope is greater than 0. So what happened here? What happened? Delta f. So this one gives us f prime. This one is greater than 0. So after integration, this one is from small to larger. From small to large. Okay? So it makes sense. Increase. Therefore, after integration, it should be this one. You can write this form or absolute value the same because this is positive. Positive. And then from here, be acceptable. Okay. Now you have an idea because of this one. Because of integration from smaller to higher, from higher to smaller is different. Okay, so from smaller to higher, we need a minus sign. We need a minus sign. Okay, therefore, different slope, the result will be different. But anyway, just take the absolute value of the slope. In both expressions above, the integration is from a smaller value to a larger value, as in the definition of the delta function. From the smaller to a larger. Okay? So compare with 2. F of delta f of x is similar to this one. It's similar to this one. If f of x has multiple roots, more than 1 root, in that case, congratulations, you need to deal with this one. And at this moment, you don't have to worry. However, if you take plasma physics, you will deal with this one. You will deal with multiple roots. Okay. You will deal with complex integration, contour integration. Okay. All your nightmare will be that will be much more difficult if you have multiple roots. Right now, don't worry. Okay. All you need to do is this one. So exercise, you can find this one. Oh, because of this property, you can easily show no difference. S minus a delta function, S minus a or a minus x, no difference. Okay, because of this one. And delta cx, we need an absolute value of c. It can be plus, can be minus. Okay, therefore, you need an absolute value of c. Okay. Okay, we have other notation. If we just deal with 1 dimension. Now, let's deal with 3 dimension. S, Y, Z. Here we prefer S1, S2, S3 because computer use 1, 2, 3 is much more easier. Okay, so we use X1, X2, X3. That's 3 dimension. We first write the Cartesian coordinate, 直角坐标系统，或是笛卡尔坐标系统。Cartesian coordinates. Delta S1 minus S1 prime. This is not derivative, just another coordinates. 另外一个坐标系统 ，delta x2 minus x prime, x3 minus x3 prime is very long. Therefore, we express as this one. Okay, it's very long, not convenient. This is a shorthand notation, very easy to write, but its physics meaning is here. So a delta function, x prime, if this one will become this one, and this one, separate into 3 terms, and each term is the Dirac Delta function. Okay, so if x prime lies outside V, nothing. on, we will consider unprime system as the source term. Prime system as the source term. And unprime system as the observer. Okay. And we should perform the integration of all the source. Okay, later we will show you, but at this point, we just show you here. That's the Cartesian coordinate. You can express the green function, delta function as cylindrical coordinate, 圆柱坐标系统。Cylindrical coordinates. Once again, you can write here. How do you know? I guess at this moment. It's not a rigorous proof. It just because this integration, rho d phi dz, rho d phi dz is the root. So you can guess. We have an extra rho here. So therefore, your coefficient is cancelled. And then, after integration, you have this term, this term, this term. 3 terms. So the leading coefficient will cancel with this one. Reasonable guess only. Okay. So it's not a proof. It just show you it looks reasonable. And we will use these reasonable techniques later. Okay. So 1 over rho, the rho minus rho prime, the phi prime, z prime. Okay, now you know this phi is coordinate. This is coordinate. And this is potential, once again. And this one is to be determined. Okay. Third, cylindrical coordinate, a spherical coordinate.球坐标系统. Once again, we have r theta, r phi theta, r theta phi. Okay. Once again, r minus r prime, reasonable. And this one is delta theta minus theta prime, delta phi minus phi prime. You can rewrite this equation into here, move to here. So become cosine theta minus cosine theta prime. Okay? And cosine theta minus cosine theta prime can be write into this form. And because theta is 0 to pi, so sine theta is always positive. Always positive. So don't worry. It's always positive in this range from here to here. Theta is the angle between the axis and here. So just 0 to pi. So that's why we can write into this form. So you have 2 expressions. One is this one. The other is this one. Up to you. Depends on the applications. Sometimes we like this one. Sometimes we like this one. Okay, keep this in mind. How to do that? Because we know this property. The volume integration is r squared, the r squared sine theta, the r d theta, d phi. We already know the volume integration sine theta will cancel with this one. Feels good. Okay? After the integration, we got the same. If 0 land outside, R prime outside the source, outside the volume V, it will be 0. Inside is 1. Okay? So you can write into this form. Integration, this one, from 0 to infinity dr, from 0 to pi r d theta, from 0 to 2 pi, from 0 to pi, from 0 to 2 pi, and from 0 to pi r sine theta d phi. Okay? And then you can, this one give us sine theta, move to here. This one give us 2 pi. This one give us 2. So give us 4 pi. 4 pi here. 2 pi plus times 2. And then this one. So the 3x is r squared sine theta dr d theta d phi, or r squared dr d cosine theta d phi. Just notation. But now you know why we write into this form. Okay. We have 3 problems now. Problem 1. A total charge Q is uniformly distributed around a circular ring of radius A. A circular ring of radius A. Radius from here to here. And infinitesimal thickness. Infinite, I-N-F-I-N-I-T-E, is very, very large. Infinitesimal, very, very small. 极小 ultra thin, ultra thin thickness. Write the charge density, rho x, in cylindrical coordinates. You can write the charge density in Cartesian coordinate, in cylindrical coordinate, in spherical coordinate. You can write charge density here. This is charge density, but unfortunately, we say rho is coordinate for cylindrical coordinate for O. We have 2 rho coordinate. Rho is coordinate, and rho is charge, volume charge density. We use the same notation. Uh-oh. How to do that? Change one. Change which one? Change it. Rho to R. Okay? So you can guess rho x is the charge density proportional to k delta R minus A, not rho minus A. Because if you write rho here, you will be easily confused with this symbol. The same symbol but different physical meaning. This rho means radius, separation from here to here. So here we will change to R. R minus A. Delta Z. This one is the same. What happened to phi dependence? Is there any phi dependence? Looks like phi dependence should be can guess there is no phi dependence. You can guess no phi dependence. So you can just assume I don't know what is the value of k, but I know at r minus a, when r equals a, we have something. When z equals 0, x, y plane, we have something. Otherwise, nothing. Okay? So we can start to find the coefficient k. Just put it inside. And we know r actually is rho d phi dz. Or change to r d phi dz. Okay? dz, nothing. Just 1. d phi gives us 2 pi. r dr, only when r equals a. So only a. So eventually k 2 pi from phi, k from here, a from here equals q. Therefore k equals q over 2 pi a. Okay? So we know the coefficient is here. The charge density can be write into this form. Okay. What's the difference between here? Row. What's the difference between these two expressions? After integration, the same. Right? Only when r equals a, we have value. So it should be the same. If you perform the integration, in this case. Okay, so sometimes people will write into this form. Some students, when you write the answer, sometimes you will write into this form. Sometimes you will express into this form. Acceptable. Okay, two expressions, but only when r equals a, because of the property of the delta function. I will stop for 1 minute. 1 minute break, or 2 minutes break. Let me show you one thing. Okay. You know, it's Professor Zhang. This lecture room is the lab space of Professor Zhang Shili. It's the lab space of Professor Zhang Shili. Zhang Shili, he is the professor of our department and professor, chairman, and dean of the College of Science, 理学院院长，物理系系主任，理学院院长 ，Vice President of 清华 University。清大副校长。At that time, I was the vice chairman of the physics department. He was the vice president of the Tsinghua University, and he becomes director of synchrotron radiation research center, 同步辐射主任。And Professor Zhang Shili and Professor Zhu Guorui, they are academician of academic syndicat, 中央研究院的院士。 三个院士，还有一个是谁？大家知道吗？鲁茂坤。他的角色比较尴尬一点。这两位院士 ，they received their honors from Alt. This is his lab space. Unfortunately, he passed away at March at the age of 72. Okay. I like him, and Professor Corey Chu is my supervisor. And Professor Zhang, my lab space is over there. And Professor Zhang's lab space is right here. So we have a cross collaborations, or we have a cross contact. He was a very friendly person. Actually, 他是我高中的学长，大我20岁。对 ，very friendly. And Professor Zhang, academician Zhang, this afternoon we have a ceremony to celebrate in memory of Professor Zhang, just outside, right in this lecture room, Okay, he is an excellent basketball player, and Professor Chu, the same. Professor Chu, he has the highest score when he entered National Taiwan University. 榜首，状元。But he said he is the lowest grade when he graduated. 第一名进台大物理系，最后一名毕业。But later on, he works very, very hard. He spent 4 years playing basketball. The same. These two academicians play basketball very intensively. Excellent basketball players for both two academicians. 院士，这两位院士都球打得很好。I like to play with him, play basketball with him, because all I need to do is get the ball, get the rebounds, and pass the ball to him. He will 3-point shot. Bingo. Yeah. I like to cooperate with him, play the basketball with him. And at that time, he is at the age of 57 or 58. But he still can run, can jump. Yeah. Very active. Very active. Okay. Professor Chu right now is close to 77, but still very active. Where's our TA? 前大家会觉得说啊，你都在打球不务正业。I don't think so。特别是最近的时候，你这个有其他的户外运动，大家都会觉得你不会再以异样的眼光在看你。所以我们这一次上礼拜办的新进人员研讨会，其实很有趣哦。我看到很多学生其实是我以前教电磁学毕业的，很多新的助理教授们、助理研究学者，是当年就像你们一样坐在下面听的人。在10年后，他们已经变成 assistant professor 助理教授。这个时候大家就敢讲出，我对什么有兴趣，我对什么有兴趣。因为我带队讲，带队跟大家讲，有兴趣的事情好多。你看我在天上飞了那么多年，飞了20多年。I am an airplane pilot for 20 years. I like cycling. I like swimming. I like mountain climbing. I like farming. 这样，所以现在大家都会讲，而且事实上我们系的教授有很多运动能力都很强，强到你会觉得有一点变态的强。有点牛。
可以举个例子吗？
我就不讲我了，我只是撑住而已。好多人很强，真的很强。你问他好了，你问问看，有些人骑脚踏车上5里的速度超快的，也超过国际上可以做的程度。有些人去跑步，还是很好的 YouTuber。而且我们系上跑步的教授还好几个。OK， 好几个，而且会打桌球、打网球、打排球、打篮球的很多，真的。所以我们会觉得有健康的运动，其实会让你脑袋更活一点，然后会让你即使失败了，知道再站起来就好。你经常会输人家嘛，天外有天嘛，对不对？打球都会输了，做研究当然也会输，失败了就再来就好，被当掉了就再来就好。十几年前有一个学生，他的成绩其实修电池的时候不太好，最后是57分。那57分通常我是不会当的，而且她还是女孩子，对不对？长得很漂亮的女孩子。我还写了好几封信，不断的催促她，你只要再补一点作业，你就会过了，因为大学嘛哈。然后她都不理我，我还叫她同学打电话给她，催她赶快来做最后挣扎一下，因为我觉得57分、58分，那个 error bar 的边缘嘛哈，是可以接受的哈，在我的 definition 是可以接受的，就她都不来，后来才知道原来跑去玩，所以别人都联络不到她。后来，他竟然跑到我实验室来做专题，而且做得不错。那后来去念博士，现在已经变成助理教授。这张调还是可以做得很好。只要你后来有努力就好。condition 是后来有努力。OK。I want to show you this one. But before that, let's assume prime is 0. So we can simplify the notation to here, to R and delta R. The first step is simplify the notation here. And definition of delta R becomes 0, becomes 1, the same. And we need to prove two things. One is Laplacian 1 over R equals 0 if R is not equals 0. Second, if this one it gives us minus 4 pi, if R 0, enclosed R is 0. Okay, give us the total volume, all the space, give us minus 4 pi. should understand. And Laplacian 1 over r, no contribution, no contribution. Only this term survive. Okay, 1 over r, so it gives us r squared over r squared. This is 1. If r is not 0, this is 1, right? This is 1. So something over something is 1. The 1, the r is 0. Makes sense? So we'll prove this one. We'll prove the first condition. The second condition is here. You change from Laplacian of volume integration to this form. And from this form, you can change to surface integration. Surface integration. That's divergence theorem. Divergence theorem tells us you can change the volume integration to surface enclose the surface. And gradient r equals to minus 1 over r squared er. This one. Er dot er. So, and this one gives us r squared d omega. Omega is sine theta d theta d phi. Okay. Let's starting angle. R squared cancel with r. Okay? So r squared cancel with r. Eventually, we got minus 4 pi. Minus 4 pi. The proof of the second property is related to divergence theorem. And related to here. Related to these properties. Those divergence theorem and related to flux. Flux. The problem of evaluating r squared over r and r equals 0. We do not have the problem because r greater than 0 on the surface. On the surface is outside. So we don't have to deal with 0 over 0. 0 squared over 0 squared. We don't have to deal with that because x is the surface. R is not equals to r, so we don't have to worry. Second, now let's change to r equals x minus x prime. Change the coordinate. Change the coordinate. X prime. So r is here. Okay? That's the major difference between Griffith and Jackson. Jackson always used x minus x prime. Griffith preferred this notation. Personally, I don't like this notation because this notation is difficult to type. It's easy to write, but difficult to type. You need to find some special character for this notation. Anyway. This one is much more easier to understand. Okay. Jackson always write it out. Always. He do not use any shorthand notation here. Okay? Problem 3 is for you. You should practice by yourself. Okay, we still have 10 minutes. I will show you here. Uniqueness theorem. We still have 2 pages to go. Uniqueness, 唯一性. Uniqueness of the solution with Dirac Dirichlet and Newman boundary conditions. We have two boundary conditions. Actually, we have three. Dirichlet boundary condition means the boundary is given, is specified. Dirichlet. Newman, let the derivative, normal derivative of the boundary is given. Normal derivative of the boundary is given. And if we have a Cauchy, and where is the Cauchy boundary condition? The third one is the Cauchy boundary condition. There's the mixture of this one and this one, or both. Okay. Newman, some people pronounce as Neumann in German pronunciation, but looks like Newman much more easier. Eventually, Newman. Okay. That's another application of the Green's theorem. We use it to prove the uniqueness theorem. How to do that? Let's consider Dirichlet boundary condition. We like Dirichlet boundary condition because it just specifies the boundary. How to specify the boundary? Easy. You just give the potential here. For example, if you have a conductor and you just ground to something, then you specify potential on the surface. So it's much easier to control, to manipulate. Okay, much easier to control from the user viewpoint. Okay. Therefore, we prefer Dirichlet boundary condition. That is, the boundary is given, or the boundary is specified by someone. Okay. And we just give, let's consider a condition. We have a volume V. And inside this volume, we have a charge distribution. And on the surface, the potential is given. So, on the surface, the potential is given. So it's Dirichlet boundary condition. And potential is here. We will solve this one. And assume we have two solutions. For example, you found a solution, phi 1. You found another solution, phi 2. We have two solutions, phi 1 and phi 2. Phi 1 must be satisfied Poisson's equation. Phi 2, the same. And on the surface, they should be the same. Otherwise, it's not a solution. So, although U2, phi 1, phi 2, and you must satisfy Poisson's equation. And you must, on the surface, should be exactly the same. On the surface. So we can define another notation, U. U just phi 1 minus phi 2. Therefore, Laplacian U will be 0 anywhere. Laplacian U will be 0. Okay? Makes sense? Because it's the same. So Laplacian U will be 0. And on the surface, 0. Everything is 0. 0, 0. Then, let's substitute phi and psi. Let's use these properties. See what will happen. Let's use this property, Green's first identity. And phi psi O equals to U. Okay? 0. The gradient U dot Remember, U is 0 on the surface. U is 0 on the surface. So this one is 0. Therefore, this is 0. And this is 0. So only one term survives. This one. After integration, this is 0. Remember, this is absolute value squared. So it should be always greater or equals to 0. It should be always no 一个正整数的平方，对不起，一个绝对值的平方，全部积分还是0。Only one solution. That is greater U equals 0. So not just Laplacian U equals 0. Gradient U equals 0 as well. That means U will be here, will be exactly 0, all different by a constant. Differ by a constant. Okay. But this is not convenient, so we prefer this one. Here we need to give Newman boundary condition. Newman boundary condition. Newman boundary condition. It may differ by a constant. We prefer Dirac boundary condition. Much easier to control from the user's viewpoint. We prefer Dirac boundary condition. Okay? So phi 1 and phi 2 differ by at most a constant. Actually, if we use Dirac boundary condition, they should be exactly the same. So we don't have to worry if a function satisfies Poisson's equations in a space and satisfy the boundary condition, then it is the only solutions. Don't worry, just satisfy Poisson's equation and satisfy boundary condition. Then it will be the only solution. That's uniqueness theorem.
这两个边界条件在实验上有没有容易做到？
当然是这个，这个只要给它电压就搞定，而且电压多容易给啊，接个 power supply 就搞定。你要给电场，你怎么给？你还要再算呢，还要再算，对不对？这是给电场，这是给电压，这是给 normal 的电场。糟糕，金属的话 normal 电场容易，啊，导体介电子呢？介电物质你怎么给？对不对？辛苦了哈、哦。所以最好旁边全部都用金属围起来，给它 ground， 搞定。
那有没有那种机车很奇怪的实验，你要是用下面这种边界条件？
我没有看过，但是我相信应该会有人吃饱撑着做这种事。一般的做实验的比较不会做这种事情。公司搞边界条件就已经够累了，所以你不会做这种事情。可是当你手上没有东西的时候，就很难讲。你可能就会搞一些 special case， 尝试看看有没有新的物理会发生。通常不会有，但是也很难讲，对不对 ？Any other questions? That's the end of today's course. Next time we will talk about green function. So green function must be satisfy delta function, and green function on the surface will be 0. Okay, that's the green function. Only 4 pages. Only 4 pages. Any questions? Our TA will show you how to solve the homework assignment later.